a limit. We have to use a limit. That's the way we get our exact value. But a table is what we just did, Hunter, is what I'm saying. That what we just did effectively is make a table of values. A table of values doesn't give us an exact answer. So for this limit, everybody, what is our a value? So for what I mean by that is we have the limit as h goes to 0 of f of what? A plus h minus f of a all over h. In this case, what is the a value? In this case, what is the a value? 1. We're trying to find the instantaneous rate of change at the a value, at an a value of 1. So we're doing the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. And the reason we do this is it doesn't give us the derivative, but it's a lot easier to solve this. If we don't have the a value in there, it's a lot easier to solve. Well, first of all, what is f of 1? You already kind of did that one, right? What is f of 1? 3 1/4, right? So end it with minus 3 and 3.25. But you have to do the function evaluated at, what is it, 1 plus 2 times 1 plus h, right? Plus 1 plus h squared over 4. You see all those 1s? What would they be replaced by if we didn't do the substitution? They'd be replaced by a's, and h goes to 0, sorry. They'd be replaced by a's, and that would be just, you can do it, and you'd have something very useful, but it's just more work. It's not asking us for the derivative, it's asking us for the derivative evaluated at one point. So what should you do at this point if you're trying to do this limit? What's the only real thing you can do at this point? What are you going to do? You just have to, yeah, well, that's a good way to say open it up. You have to multiply it out. Yeah, you have to multiply it out. There's no, is there any cool like trig identity or something we can factor there? No, you just actually have to do this out. And what are you hoping cancels? You really want that h to go away because you can't plug in 0 for h as it is right now. So let's do some of this algebra. To reiterate here, this gives us the derivative at a specific value. This is not the derivative function. This is the derivative at a specific value. If we wanted the general derivative, we wouldn't have plugged in 1. We would have kept in what? A. Remember we made that mistake like last week where we tried to find the general derivative but we had plugged in a value and it didn't work? Well, of course it didn't work because it only works for that value. It's a lot easier to do this though because we didn't have to factor anything. We didn't have to deal with a value. Ready? Hold on. Let's just do the simple stuff first. So we know that it's negative here and it's negative there. So we know it's below the x-axis there. And we also know that it is positive here and positive there. And now I did add in this new thing. Where is it steepest? We know it's steepest here and there, right? Do you agree with that? It is like most negative and most positive at those points. Do you agree that those blue dots are where it's steepest? So we know that it's going from positive to negative right here. So we know it's going to go, it crosses down, right? It's going from positive down into the negative below the y-axis. And then we know it's going to cross and go up here, and it's going to go down like that, correct? But the blue dots also represent where it's going to be the highest at that x value. So what is this going to look like? It's going to look like that. It'll look like that, and then it just goes down like this.
Wait, but why is it lowest at that one blue dot?
At this blue dot right here, listen. You see this if you're on the roller coaster right here? Where is it steepest? It is most negative right there. So it has to be most negative right there. It is most positive here, so it's going to be most positive right there. Exactly, right. So let's do the next one. So this next one right here, Adam, you're absolutely correct in your observation. Something interesting happens on this one. First thing you recognize is that it definitely crosses there and maybe right there, right? Do you agree with that? So it's negative here, so I'm not going to do this. I'm not going to divide this up. It looks like it goes something like this first. It goes up, and then it comes down, right? And then it's negative and positive.
Doesn't jump.
Now here's the thing. Is the slope positive or negative right there?
Positive.
It's positive, so it's going to keep on going up. Do you agree?
Yes.
What does this look like right here? That's a line, right?
What does that point mean?
Okay, hold on. Let's just finish this. What does that slope? That looks like a line, right? So it looks like it's a constant slope. It's like a negative. That could be -1, right?
Oh, okay, I'm so confused. Oh,
Okay, so these points have. Do you understand where these points came from?
Well, yeah, but what?
Okay, I'm now stop. I'm going to do this in pieces. This represents where the slope is what? Negative. So it has the part of the derivative has to be below the x-axis right there. Do you see the red line, how it's below the x-axis right there? Okay, then we did so it's negative there, and we also know it's negative right here because it's going down on that little section. For the positive parts, we know we know the graph is the rate of change is positive there. Do you agree?
Yes.
Oh, I highlighted the wrong thing there. Sorry. That should be. I shouldn't have highlighted the red. I should have highlighted this right here. We know that's negative from there to there, right? And then what happens? It goes positive again, and then it turns back to negative right there. So wherever the graph is, the slope is negative, the red line has to be below the x-axis. Wherever the line is purple, it has to be above. But look at what happens. Something really interesting happens right here. It instantaneously changes derivatives. There's a kink. That's the definition of a kink. It instantaneously changes derivatives. So look, right here, the derivative is getting steeper and steeper. So what happens to the graph of the derivative? It gets higher and higher. But then all of a sudden, instantaneously, it changes to a slope of -1. So what can you say about the continuity of the derivative? Is the derivative continuous?
Yeah.
No, the derivative is not continuous. Root x over root x plus 1. Now, what factor on this thing, what factor are we really trying to get rid of in there? The one on the bottom, right? Do we really care what's on top? No, we just really want to get rid of that root x minus 1 because we can't plug in 1 there, right? So yeah, here's another method. Multiplying these out is a little messy. Just remember that cube root of x is equal to x to the what? X to the 1/3. That's all you really have to remember. You can try this out. Both of these might get you somewhere, and I will tell you that it is possible. It totally is possible to do this by you multiply by a form of 1, and you end up with something where you can cancel this out right here. This is really helpful. I'll show you what I mean. Like this one right here, you look at this and you're like, okay, let's do this out. So what does it turn into? I'm not going to multiply the numerator out because do I care what the numerator is? No. Can the numerator be 0? Sure, it could be, but we don't know if it is. Over what? What's it turn into? X. Yeah, it's just x minus 1. This is nicer, right? But the problem still is, what do we have to cancel? X minus 1. And it takes a little while to figure it out. What I'm actually going to do is I'm going to give you